Alright friends, today we're talking about absolute value functions, and in the past we've talked about absolute value equations and the fact that the absolute value, because it can turn multiple expressions into the same positive number, some absolute value equations had multiple answers. We're going to see something similar happen with absolute value functions, and again, that whole idea of turning the absolute value expression to zero, finding that minimum, that's going to be important again. So let's see what we're talking about. And I have a little example. You don't need to do it with me, but I'd love it if you would just write it out, or not write it out, watch it and work with me. So we'll do our normal points and see what happens. -2, -1, 0, 1, and 2. So if I plug in -2 for x, I get -4 on the inside. The absolute value of -4 is 4. 4 minus 3 is 1. If I plug in -1, I get -2 on the inside. The absolute value of -2 is 2. 2 minus 3 is -1. If I plug in 0, we get 0 inside the absolute value. 0 minus 3 is -3. If I plug in 1, we get 2 on the inside. The absolute value of 2 is 2. 2 minus 3 is -1. And if I plug in 2, we get 4. The absolute value of 4 is 4. 4 minus 3 is 1. So what we notice is we have some symmetry here. We know that if we have -2, 1, we have this point. If we have -1, -1, we have this point. 0, -3 down here. 1, -1, and 2, 1. Those are our 5 points that we just came up with, and it looks like this would show us our graph. And we can see that there's this symmetry. We know that this absolute value means that we can't just go as negative as we want. The most we can do is go down to -3, because we could have 0 as the positive value or the 0 value coming out of the absolute value, and then we would subtract 3, but we couldn't have a negative to take 3 away from. So that kind of puts a limit on how negative our y could be. And that's what absolute value functions do, is they reflect like this at their minimum or their maximum that this absolute value makes them take on. So let's see what are some notes that are going to help us to solve any sort of equation like this, or any sort of problem like this, and to help us graph it. So absolute value functions can be plotted with an XY chart, so they're just like normal, and we just saw that. But the minimum magnitude for an absolute value expression, so the expression inside the absolute value, the minimum value is 0. So that's what I was just talking about, the fact that we can't go as negative as we want, and other times we won't be able to go as positive as we want. It kind of sets a limit on us. And so where does that limit occur? It occurs at the vertex, and that's whatever x value makes the expression inside the absolute value equal to 0. So that's really the crux of it. The main idea here is understanding the vertex, and that's whenever the inside of the absolute value is 0, that's when things are going to kind of reflect, because we'll have positive values on the inside, and those will stay positive. But then after we go to 0, we'll get negative values on the inside of the absolute value. The absolute value will turn those back to a positive. So the vertex is the point of symmetry. It's kind of where it seems like it bounces or reflects off that wall. And what do we need to know the vertex? What do we need to know about this for? It's going to make it easy to graph. We want to know where that point is so we can extend rays in both directions, like you saw in that first example problem I showed you. So to graph these functions, we should plot the vertex and then points with bigger and smaller x values. So we want to find points on either side so we can extend both rays from the vertex that go in different directions. Let's get to an example problem. This one says y equals the opposite of the absolute value of x minus 1 plus 13. So like we said, we're just going to use an XY chart. And the first point we want to find is the vertex. So what's our vertex going to be? We said the vertex is the value, the x value, that makes the inside of the absolute value equal 0. We want to see where is that minimum or maximum. And we'll see which it is in this case. What is going to make the inside of this absolute value equal to 0? Well, if we plug in 1 for x, then we'll do x1 minus 1, and we would get 0. So what do we actually get? If we plug in 1 minus 1, we get 0. The opposite of 0 is 0, and 0 plus 13 is 13. So when we plug in 1, we get 13. We need to choose a bigger and a smaller x value. So let's do that. Let's do 0 and 2. That's easy enough. So if I plug in 0, 0 minus 1 is negative 1. The absolute value of negative 1 is 1. But then the opposite of that is, again, negative 1. Negative 1 plus 13 is going to be 12. And let's see about this. 2. 2 minus 1 is 1. The absolute value of 1 is 1. But the opposite of that is negative 1. Negative 1 plus 13 is, again, 12. Okay, so our vertex is at 113. I'm going to need to change the scale. Let's make it 2. So at 1, and then we're going to go up to 13. That'd be 2, 4, 6, 8, 10, 12. So it'd be right in the middle between 12 and 14. That's our vertex. I know things are going to reflect in different directions. So at 0, 12, we're actually right down here. And at 2, 12, we're right over here. So this is an example. I want to make sure I'm drawing this well. This is an example of an absolute value function that really doesn't have a minimum y value. It has a maximum. And why is it a maximum y value? Is because this is going to be negative. We're switching the sign of whatever we get out of the absolute value. So we'll have 13, and then we're adding it with some negatives. So it's going to get lower. But what's the least amount of negatives we could have is 0 negatives. So the maximum y value is 13. So this is an example of an absolute value function that opens down. We call that opening down if it extends infinitely downward. Obviously that first example isn't one that opens up. And you'll see that it's this lead coefficient in front of the absolute value. That's going to tell us whether it opens up or down. Let's see another example. This one says find the vertex and graph, and I made this one a little bit more annoying. I wouldn't do this to you in your practice problems, but they're kind of fun to do together, so let's see what we get. Let's make this more manageable by using our equation solving or our equation manipulation steps. I could subtract 7 from both sides. That makes sense. We're getting y by itself because I know a lot of people like slope-intercept form. So 2y equals 4 times the absolute value of 2x minus 3, and now it's just plus 2. The last thing I have to do is I have to divide both sides by 2. That'll make things easier. If I'm going to divide the entire left side by 2, I have to divide the entire right side by 2. And we'll just get y is equal to 4 divided by 2 is 2 times the absolute value of 2x minus 3. Oh, absolute value. And 2 divided by 2 is 1, so we're just going to add 1. Again, XY chart, and first we need to find that vertex. So what's our vertex in this case? It's the value, oh, I don't like this at all. Okay, it's okay. It's the value that of x that makes the inside here equal to 0. So 2 times what minus 3 is going to equal 0. That'll be our vertex. And something to think about here, what I'm thinking about is I'm saying, okay, I'm going to multiply 2 times something, and I want it to be equal to 3, because 3 minus 3 is 0. 2 times what equals 3? You could say 1.5, or you could just know that, well, I know that I want 3 to be the numerator, and if I'm multiplying, then 2 could cancel a denominator of 2, so 3 halves. When 3 halves is x, we get 0 inside here. Absolute value of 0 is 0. 2 times 0 is 0. 0 plus 1 is 1. Now let's choose some easier x values. We need a smaller and a bigger, so I'll choose 0, and we'll do 3 as well. Those will work. It won't be symmetrical points because they're not the same distance. Oh, they are. They are the same distance. Oh, so they'll be symmetrical. Okay. 0 times 2 is 0. 0 minus 3 is negative 3. The absolute value of negative 3 is positive 3. 3 times 2 is 6. 6 plus 1 is 7. Now what about 3? 2 times 3 is 6. 6 minus 3 is 3. The absolute value of 3 is 3. 3 times 2 is 6. 6 plus 1 is 7. So I know at 0 we can go up to 2, 4, 6, 7. 0, 7 is a point. I know at 1.5, 1 is a point. 1.5, 1. And then at 3 we're back up here at 7. So this is a lot sharper. There's a lot sharper slope. Oh. Of each of these rays. And I'm drawing poorly, I'm so sorry for that. But hopefully the process is making sense. Find that vertex, a bigger number, and a smaller number for x. Find out those y's and just plot those points and connect them. I don't know if we have another one. I think we're good. Practice. This is for you. Name the vertex for the function y equals 7 plus the absolute value of 2x minus 8. Just name the vertex for that one. That should be a point. And then number 2 is find the vertex and then graph. So y minus 7 equals negative 3 times the absolute value of x plus 2. Best of luck. You're going to do great. Find that vertex and a bigger and a smaller number. And I'll see you later.